After studying about the Gauss law, here's the time for us to find the electric field intensity due to various charges. Now, we already have studied about the calculation of the electric field intensity at various points. Here's the time to start with some complex situations. In this condition, the first derivation or the first study that we have to do is to find the electric field intensity due to the long, infinitely large, uniformly charged wire. Now, this is a long term, but it does not mean a very long definition. In this condition, we have to find the electric field intensity, as we already know about it, due to infinitely long. That is, the length of the wire is very, very long. So, we have considered it as infinitely long. Now, the other term is uniformly charged. What do you mean by uniformly charged? Uniformly charged means that the charge is distributed over the length of the wire equally. That is, if we have to find at every point the charge distribution, then it gives the equal distribution. Now let me demonstrate you with a very simple diagram. In this condition, suppose this is a wire, okay? This is a wire which is infinitely long. If it is infinitely long, so the length of the wire is also very, very large, which is shown by the dotted line. Now, the second is that it is uniformly charged. That is, the charge is distributed across the length of the wire uniformly, that is equally. Now, it is given to you that you have to find the electric field intensity at point P, and this point P is at a distance, let's say small r, from the center of the length, which is represented by capital O. So the distance OP is given to you r. So this is all given to you. You have to find the electric field intensity at point P. Now let's start with the derivation. For this derivation, first we have to consider a cross-sectional part of the wire. That is, it is the infinitely long wire, but we considered the 2 points. Let's say the first point is P1 and the second point is P2. So P1 and P2, between P1 and P2, the length of the wire is fixed. So that's why I am talking about a cross-sectional portion of the wire. Now we have to consider the electric field intensity due to P1 and due to P2. Now look at the diagram. Due to P1, it exerts the electric force at point P, and this electric force is in this direction. So the electric field intensity is directed outward. It is represented as, let's say, E1. Similarly, P2 also provides some electric force at point P, and similarly P2 will exert the electric force which is directed outward like this. It is represented as, let's say, E2. So these are the two electric field intensity which is created by P1 and P2, as we all have studied about it. Now we have to resolve E1 and E2 into their respective components. Like for example, if suppose this is a horizontal line and this is a vertical line. So the horizontal and the vertical line are the x-axis and the y-axis, okay? E2. This E2 is making an angle, let's say theta 1 with that of the x-axis. Similarly, E1 is making an angle, let's say theta 2 with that of the x-axis. But P1 and P2 both are same points, okay? So electric field intensity, that is E1, is equals to E2. If E1 and E2 are same at point P, so that means theta 1 and theta 2 are also same. So we can write that E1, E2 is equals to E. Similarly, theta 1, theta 2 is equals to theta. Now, if we have to resolve E2 into the y-axis and the x-axis, this is the x-axis, so it becomes E2 cos theta. Similarly, this is the y-axis for E2, so it becomes E2 sin theta. Similarly, we have to resolve E1 into its two components, so it becomes E1 cos theta. Similarly, this axis becomes E1 sin. So you can see here that we resolved E2 and E1 into their two components, cos theta and sin theta. Now if you have to find the resultant, that is at x, the resultant x you have to find, then you can see E2 cos theta and E1 cos theta, both are going in the opposite direction. This is the direction in which they are going. So we need to subtract E2 cos theta minus E1 cos theta, as E2 and E1 both are equal and theta are also equal, that is theta 1 and theta 2. Here due to theta 2 this forms with theta 2 and this is also theta 2, theta 1. Okay, now you can see here that the theta 1 and theta 2 both are same. So we can write from here that E2 and E1, E cos theta minus E cos theta, both becomes equal, so they cancel out and your answer is 0. Similarly, if you have to find the resultant at y-axis, so you can see E2 sin theta and E1 sin theta, both are going in the same direction, so they need to add up. Okay, I am adding it directly, that is, it becomes now 2 times of E sin theta, and this 2 times of E sin theta is called EY. Now, this is what we have calculated, and from this I have to draw a conclusion that the resultant at point P is radial. What do you mean by the word radial here? The radial means the ray which are diverged outward from a particular point, that is from the center. This radial is similar to the radius of the circle. So I have told you that the resultant at point P. What is the resultant at point P? The resultant at point B becomes EY because EX is 0. So what will be the resultant? It only left is EY. So the resultant at point P, that is EY, is radial. Radial means directed outward from the center point. And you can see here E1 sin theta 2 and E2 sin theta 1 are also directed outward from the center point. So we have concluded that the resultant is radial. Now, if we have to find the electric field intensity and the Gauss law is applicable to it, so in that condition, the important thing that you have to keep in mind is that you have to consider a Gaussian surface. Okay, now let's first start. What is a Gaussian surface? Gaussian surface is a surface that is closed surface. Okay, I am talking about the 3D closed surface. Now there is one word attached to it that is very common, and the word attached to the Gaussian surface is symmetry. Okay, now let's first understand what is this symmetry. Symmetry means equal at all points. Okay, like for example, suppose this is a particular area, my hand is particular area, and the electric field strikes here. Now you can see that if any point electric field strike at this point, at this point, at this point, at this point, at all points you will get the same electric field intensity because my hand is symmetrical. Okay, so the electric field intensity is also same. Put my hand like this. Okay, if I curve my hand, then in that condition you see now the electric field strike here, the electric field strike here, the electric field strike here. So do you find the same angle here? No, you will find that at this particular position the angle is different, at this particular position the angle is different, while at this particular position the angle is different. So that means this surface is not symmetrical. So symmetry means same at all points. So if we have to consider the Gaussian surface, so we have to take the symmetry into consideration. Now, like for example, I already told you that cuboid, spherical, cylindrical, these all are the Gaussian surface. Okay. For example, if I first talk of cuboid. In the case of cuboid, you can see this is a symmetrical surface. If the electric field intensity strike at any point, you will get the same value. Similarly, this is also a symmetrical surface because the electric field intensity is same at all points. Likewise, this is also a symmetrical surface because the value is same. But if I ask you that is this surface and this surface, both surfaces are symmetrical to each other, then your answer is no, because at this point you will find that the electric field intensity has a particular direction like this, but at this point the direction is changed. So these are symmetrical but individually. If you ask and you compare the two surfaces and you will say that first surface, second surface, third, fourth, 5 and 6, are these 6 surfaces symmetrical to each other? Then the answer is no, they are not symmetrical to each other, but they are individually symmetrical. So this is the meaning of what I am talking about. But the Gaussian surface has given us the permission to make a Gaussian surface by combining 2 or more symmetrical surfaces. Like for example, cuboid is considered as a Gaussian surface because in this it is formed by combining 6 symmetrical surfaces. So this is the permission which is granted to you, that you can take two or more symmetrical surface and you can combine it to form a closed surface, and this becomes a whole Gaussian surface, but it is not symmetrical at all points. So just mark the difference. Now, if I talk of, let's say, spherical, okay. The spherical is basically a circle with a particular volume. So in this condition, you look here, this spherical is symmetrical at all points. It is not formed by combining two or more spherical surfaces, but it is symmetrical at all points. So it is good for us if we go into the spherical portion of it, because we don't have to consider two or more or six symmetrical surfaces. In this, whole sphere is a symmetrical surface. So the sphere is called that this is spherically symmetrical. Similar is the case for cylinder also. If you have seen the cylinder, okay, it looks like this. This is a cylinder. Now, you can see here that this portion, this longitudinal portion is symmetrical at all points, and these two edges, this is the first edge and this is the second edge, these two edges are also symmetrical. But if I ask you that are these three areas or are these three surfaces, that is first, second and third, are these first, second and third surfaces symmetrical to each other? No, they are not symmetrical to each other, but individually if I talk about, then first surface is symmetrical, second surface is symmetrical, third surface is symmetrical. So Gaussian surface is also a surface which is formed by more than two symmetrical surfaces. That's why this cylinder is also considered as a Gaussian surface. Now, this is all about the Gaussian surface, but the Gaussian surface is applicable only in particular conditions. Now let's see what are these conditions. As I've already told you that sphere is a Gaussian surface. Okay. Now if I place any longitudinal charged body inside this sphere, like for example if I place a wire which is uniformly charged inside the sphere, then can you consider this sphere symmetrical with respect to this wire? No. Why? Because if this wire is projecting the electric field outward, then at this point, at this point, at this point, you see that the electric field intensity is different. So we can say so that if we talk about the longitudinal length of the conductor, then in that condition, this sphere is not considered as a Gaussian surface. Now take another example. If I consider a point charge, if this is a point charge, it directs the electric field in all directions. Now you can see, as the sphere is symmetrical at all points, so the electric field intensity created by these point charges are also symmetrical at all points. Here you will find the same value of the electric field intensity. Here also the angle is same angle. At every point of the sphere, the angle is same. So we can say so that the sphere is considered as a Gaussian surface only for point charge object. So this point is very important for you, that the sphere is considered as a Gaussian surface only for point charge body. Now let's move on to second point. If for example, just remove this sphere. Now the same point charge, if it is placed inside a cuboid, this is a cuboid, okay. If the same point charge is placed inside the cuboid, then will this cuboid also act as a Gaussian surface for this point charge? Now let's see it. It produces electric field in this direction, produces electric field in this direction. Okay, now if it produces the electric field in this direction, you can see at this point 90 degrees, at this point 90 degrees, so it is good, they are equal. But at this point it is not 90 degree. That means it is not symmetrical. So the cuboid is not symmetrical for the point charge body. This I have shown you in order to prove that all surfaces are not Gaussian surfaces. The spherical, the cuboid, the cylindrical are a Gaussian surface, but with particular conditions. And the condition is that sphere is only a Gaussian surface for point charge body, but it is not true if we come to the case of cuboid. Now let's see the third Gaussian surface, that is a cylinder. This is a cylinder, okay. For this cylinder, let us consider a charged body in which the cylinder acts as a Gaussian surface. Now, if we put a line charge, okay, this is a line charge or a length of wire inside this cylinder, then you can see at every point you will find the same electric field intensity. At this point, if you notice, the same electric field intensity at this point also, even at this point also, at this point, at every point if you calculate, you will find the same electric field intensity. So, a second point is that the cylinder acts as a Gaussian surface only for line charged object, and it is also applicable for line charge as well as for plane sheet of charge. If we place any plane sheet of charge, this is a plane sheet of charge where the positive charge is distributed all over, and for this particular condition also the cylinder acts as a Gaussian surface because it produces the uniform electric field intensity at all points of the cylinder. So this is the second point, that the cylinder acts as a Gaussian surface for line charge as well as for plane sheet of charge. So these are the 2 points that define easily what is a Gaussian surface. Before studying further, first you have to study by heart what is a Gaussian surface. The Gaussian surface is applicable only for specific charged body. In the condition of sphere, it is point charge. In the condition of cylinder, it is line and plane sheet of charge. Now, considering the concept of the Gaussian surface, we have to find the electric field intensity with respect to this infinite, long, uniformly charged wire. Now, if this is a point P, at this point, as I've already told you, we have to find the electric field intensity which is placed at a distance r from the point O. Now, the first point that you have to remember, as I've already told you, that for every charged body, you have to first find out the Gaussian surface. Now, for this long charged wire, the Gaussian surface is, I've already told you, that is a cylinder, okay? So now we have to consider a cylinder which is placed around this particular charged wire. Now let's find out what is the electric field intensity. In that condition, if this is a point P, consider a very small portion of this cylinder. This is a very small portion of the cylinder and the cross-sectional area of this cylinder is ds. If we have to find the area vector, so the area vector is always perpendicular to the particular area and that too directed outward. So this is the area vector given by the cap, that is a unit vector. Similarly, if we have to find the electric field intensity which is created by this charged wire, so what is the direction of the electric field intensity? The electric field intensity created by this charged wire is always outward. So this is how the electric field intensity is created by this charged wire which is placed inside the cylinder. Now, if any charged object is placed inside any closed surface, so what is applicable? We have to move into the Gauss law. So now it becomes a part or an example of a Gauss law. Now, moving on to that particular portion, we have to consider all the symmetrical surfaces. In the case of cylinder, the cylinder is made up of 3 symmetrical surfaces. The first symmetrical surface is this. This is the curved portion, and this is the second portion, that is the edge, and this is the third portion, that is the end edge. So there are 2 edges of the cylinder and the one is the curved surface. So you have to consider all the symmetrical surfaces one by one. Now let's first start with the curved surface. In the curved surface, apply the Gauss law. According to the Gauss law, the flux is given by, this is the formula for the flux, E dot ds, and the Gauss law is q upon epsilon naught. Now, if we generalize this formula, then it becomes integration E dot ds dot cos of theta. This is all what we have studied. This is about the flux. Now you can see this is the curved portion of the cylinder. The electric field is directed outward. This is the direction of the electric field, and the area vector is also in the same direction. So what is the angle between E and A? Between E and A, the angle is 0 degree. That is cos theta. Instead of cos theta, you are going to put cos 0 degree, and cos 0 degree is 1. So in this condition, your answer is E dot ds. Okay, this is the closed integration dot 1. This is the flux. Now, if we move this closed integration towards the portion that is ds. ds is the cross-sectional area of this smaller portion. If we are doing the integration of it, so that means we are adding all ds, okay? 1 ds, 1 ds, 1 ds. These whole ds are added up in order to make the whole area of the cylinder. So this integral of ds is called the total area of the cylinder. And this is given by the formula that is 2 pi r L. Okay, now this formula is known to you. If you put the value directly, so you will get flux here, that is E into 2 pi r L. So this is what we have calculated. Now for the second, this is the first case, that is for the curved surface area. The second is the portion when we have to consider the edges. Now in the edges, you can look here. This is an area, okay, this is a area. So in this condition also the area vector is directed outward. Similarly for this edge also the area vector is perpendicular and directed outward. Now what is the angle between the electric field intensity and the area vector? You can see here, this is the direction of the electric field intensity. Similarly, this is the direction of electric field intensity. The angle between them is 90 degree. So now here it is theta is equals to 0 degree for the condition of a curved surface. For the edges, if we are talking about, so theta would become 90 degree, and cos 90 degree is what? It is 0. So in this condition, if we have to calculate the flux like we have calculated here, so the flux in this condition comes to 0. Now if we have to find the total flux along this whole cylindrical surface, then it becomes only due to the contribution of the curved surface. No edges are required, because in that condition the flux is coming 0. So now the total flux is equals to the flux created by the curved surface, and this flux is coming, that is E dot 2 pi r L. Now if we combine the flux with that of the Gauss law, so it becomes flux is equals to, it is coming E dot 2 pi r L is equals to Q upon epsilon naught. Now you can see, if you remember the derivation, that is the continuous distribution of charges, in that condition there were three parts. The first part is the line charge density, which is coming lambda is equals to Q upon L. The second part is the surface charge density, sigma is equals to Q upon area, and the third is the volume charge density. Okay, now these two are very important for us to remember when we proceed for the derivation. Here we are considering the line charge. The wire is a line, so we have to consider the line charge density. And what is lambda in this condition? The lambda is a linear charge density. Put the value, that is lambda equals to QL, and apply this value into the Gauss law. That is, instead of Q, we can put here Q is equals to lambda into L. Now your formula modifies to E into 2 pi RL is equals to lambda L upon epsilon naught. We have to find electric field intensity, so rearrange the equation. It becomes lambda L upon epsilon naught 2 pi RL. This L and L get cancelled out, and your answer is lambda upon epsilon naught 2 pi R. So this is the electric field intensity which is calculated for the infinitely long uniformly charged wire.